All right, let's take a look at some numeric methods. And the first numeric method will be a root finding method, and it's called fixed point iteration. So first of all, numeric methods are techniques and algorithms that give us an approximate solution to a mathematical problem. And what we do is we take advantage of the computer's ability to do computations very quickly, and we generally implement some kind of iterative algorithm. And the reason why we would want to use a numeric method is because sometimes the analytic solution is impossible to find. So a mathematical problem might not have an exact solution, okay? Or that exact solution might exist, but it could be really, really difficult to get, okay? And it might take a really long time for us to compute exactly. And so a numeric method is basically just kind of a compromise that says, you know what, I'm okay with an approximation, right? I only need it to be accurate up to, 5 decimal places of precision, and that's good enough for me, okay? And so, numeric methods take advantage of the computer's quick ability to do calculations quickly, and we get approximate solutions. So, for example, the standard normal distribution, the cumulative distribution function for that, okay, that is, when you integrate the PDF of the standard normal distribution, say from negative infinity to, wherever z is, there's no closed form solution for it. So I think that was probably covered in, say, Stats 100B, your mathematical stats class. There's no closed form solution for it. But you want to type into the computer into R, you want to type in something like P norm and get a value, what proportion is less than, 1.28 or something like that. And so your computer implements an approximation, okay? There's actually a little function that was developed back in the 1990s that gives us an approximation. And this is good enough because this approximation is accurate up to, I think, 16 decimal places. And that's good enough because, as we learned when we were dealing with floating point numbers, our floating point numbers on the computer are only accurate up to 16 decimal places anyway. So if our algorithm is able to, or, our computational method is able to give us an approximation that's accurate up to that amount, then that's about as good as we're going to get, okay? And that's fine, okay? So the first kind of class of numeric methods that we're going to look at are root finding methods. And root finding methods are used to find the roots of a function, or basically where the function is equal to 0. So we're assuming we have some kind of function f, and this is a function that takes in real numbered inputs and returns real numbered outputs. So not a complex function, no imaginary numbers or anything like that. So real numbers go in, real numbers go out. It's just one number goes in and one number comes out. Okay, and we're going to say a root of the function, that is x is a root if f of x is equal to 0. Okay, and so another way you can think of it is that if you were to graph the function, it's where the function crosses the x-axis. Okay, and a lot of mathematical and statistical problems can be expressed in terms of the root of a function, so a lot of these functions do have applications. Okay, so let's say you have a quadratic polynomial, okay, and it's in the form f of x is equal to ax squared plus bx plus c. Well, we could figure out the roots of this by using the quadratic formula, right? X is the roots are at negative b plus or minus this root of b squared minus 4ac over 2a, and that will give you the roots of a quadratic polynomial, okay? And so in that case, we have an analytic solution, and that's easy, and you should definitely use the analytic solution if you're able to. Okay, so in general, if you have the analytic solution, just use that. Okay, but sometimes the analytic solution is difficult to get, and in those cases, we might consider using a numeric method. All right, I'm using some references here. There's a textbook that you can download for free, and it's available as long as you are connected to the UCLA VPN. Okay, and then these are also just some additional notes on numeric methods here. Okay, so let's talk about fixed point iteration. So in fixed point iteration, we have some function g, and the fixed points are where g of x is equal to x. So this is different from a root, okay? Basically, imagine the line y equal to x, so this diagonal line that runs through the origin with a slope of 1, and a fixed point is basically where this function, g of x, crosses that line y equal to x. And, kind of a useful property of fixed points is that they remain fixed even after you iteratively apply the function, an arbitrary number of times. So if you do have a fixed point x and you apply the function g to it, okay, then g of x is equal to x. And if you apply the function to it multiple times, like g of x or g of g of g of x, they're all going to equal x, okay? That's what it means to be a fixed point. Sometimes we have fixed points that are attractive fixed points, and fixed point iteration takes advantage of the idea that attractive fixed points exist. So a fixed point is attractive if you can start off at any kind of arbitrary value x that we'll just say is, quote, close enough to your fixed point a, then as you apply the function repeatedly to x, so you start off at x and then you do g of x, and you take that result and you apply g of that to that, so you have g of x, and then you apply the function g to that output as well. Eventually, it will converge to a. If that's the case, then that is an attractive fixed point. Okay. A more formal definition of an attractive fixed point is that we'll say g to the n, or g super n of x, denotes kind of applying the function g n times to x. And a fixed point a is attractive if there's some interval I around a such that if x is an element of I, or x is in I, then g super n of x is also in I for all n greater than 0. And then for all x in that I, then g super n of x will converge to a as n approaches infinity. That's the definition of an attractive fixed point. Okay, so an example of an attractive fixed point is the square root function. We have an attractive fixed point at x equal to 1. And so you can see this, you can enter into the calculator any number you want. And then if you take the square root, so what is this? This is 15,748,945,000, etc. Okay, if I take the square root of that, I get the number 125,494. I take the square root of that, I get 354. Square root of that is 18.8. Square root of that is 4.33. Square root of that is 2.08. Square root of that is 1.44. Square root of that is 1.2. Square root of that is 1.096. Square root of that is 1.04679. 1.023 is the square root of that. And if I keep applying the square root, you'll see these numbers get closer and closer. So now I have 1.000055. And if I keep taking the square root, this thing gets closer and closer and closer to 1. Okay, and you can imagine that as we continue to take the square root, indeed it will converge to 1. So we have an attractive fixed point of 1. I could start off with really small numbers, right? 0.00000002 or whatever. I take the square root of this. Okay, now I get 1.4 times 10 to the minus 9, 3.76 times 10 to the minus 5, 0.006, 0.078, 0.279, 0.528, 0.727, 0.852, 0.923, 0.9609, square root of that is 0.98, 0.99. And as I take this more and more square roots, I get something like 0.9999999, and we can imagine that as I continue to hit the square root button, we're going to get closer and closer and closer to 1. Okay, so 1 is an attractive fixed point of the square root function. Okay, and no matter and this attractive fixed point kind of works for the entire domain of x. So anything where x is greater than 0, as long as you're putting in, if you put in any kind of value here, all right, it's going to, as long as you keep applying that function, it's going to get you closer and closer and closer to 1. Okay, so it converges to 1. So, so fixed point iteration, we can find a fixed point, all right, is that we start at some initial value x sub 0, and then we apply g to that value, g of x sub 0. We're going to use that as the value at x1. And then the next thing is we apply the g to the function g to that output x1, and that will give us x2. And we just kind of repeat this forever and ever. Okay. To avoid iterating forever, we'll stop when the difference between our current value and the previous value, okay, that is x at time n and x at time n minus 1, is less than some epsilon, some tolerance. So we just, maybe you'll pick like 10 to the minus 5, right? If the difference between our current value and the previous value is less than, 0.00001 or something, right? 10 to the minus 5, maybe we stop, all right? Maybe you want to choose 10 to the minus 6 or 10 to the minus 2. It depends. It depends how big your initial number is and kind of the value of your fixed point, what tolerance level you want to choose, okay? So that's fixed point iteration. That will help us find fixed points. And so here's an example. I've got the square root function in blue. I'm going to start off at 10, okay? This line here represents the line y equal to x, and this is where x equal to 1 and y equals 1. This is the fixed point. And so if I start off at 10, what is the value of the function at 10? The value of the function at 10 is 3.162. So what we're going to do is I kind of follow that line over. So this is 3.162 in the y direction, and it runs into y equal to x. So this vertical location, this location right here, is where x is equal to 3.162, right? So I'm putting in 10, it outputs 3.162. According to the blue line, I want to plug in 3.162 as my next x value. So I'm going to start here, okay? So at the next x value, I start off at 3.162. What is the square root of 3.162? Okay, so I say, all right, let's see where at x equal to 3.162, the square root function says that is 1.778. Okay, that's right here, 1.778. And so I want to plug in 1.778 in as my next x value. So I'm going to trace, go over at 1.778. It runs into the line y equal to x here. So this is the location, 1.778 in the y direction and 1.778 in the x direction. And so we will use this location right here. This is 1.778 for x. That's right here, and we'll plug that in. So I plug that in, and that takes me to here, 1.33. So I want to plug in 1.33 in for x. So that's going to be, this is when x is 1.778, y is 1.33, and now I want to find where x is 1.33. So that's going to be right where it runs into this line. This is going to be x equal to 1.33. I plug that in, and if I keep going over and over and over after about 15 iterations, I'm really close to x equal to 1. I'm at 1.00007, okay? And so we can see that, eventually we will converge to x equal to 1. So that's how we would go about finding a fixed point. So so now using just that method of just kind of plugging in the output into the function again, and repeating that process over and over, that's going to help you find a fixed point. Now, how do we use that technique to then find roots? Okay, because that's what we want to do. We want to find the roots of a function. Okay, so the idea here kind of goes like this. Let's say you have a function f, and you want to find the roots of the function f. So what we have to do is we have to figure out another function, g, so that when g of x is equal to x, it's also going to be the same location where f of x is equal to 0. We want to find the roots of f, we need to find another function g so that the solution to the fixed point of g is the same as the root of f. So one possibility is you just let g of x equal to x minus f of x, okay? So we'll say this is one possibility. We can say g of x is equal to x minus f of x. And so you can see that f of x is going to equal 0 when g of x is equal to x, right? So just kind of by solving this, you can say, all right, when g of x is equal to x, that's going to be exactly the same location where f of x is equal to 0, okay? And so now we can find the fixed points of this function, x minus f of x, and that's going to give us the roots of f of x, okay? Now there's there's kind of infinitely many ways to figure out a pair of functions where when f of x is equal to 0, g of x is equal to x, and in practice, some of these kind of different ways will be better than others. Some will work and some won't. So here's an example function, okay, and we'll see this function appear in future videos as well. But let's say this is the function and we want to find the root of this function. So we've got f of x is equal to log of x. This is natural log of x minus e to the negative x. And we want to find where does this thing equal 0. Okay, where does this thing equal 0? So one thing I can do is I could try to solve for x, and then so I'm going to set this equal to 0 and I'm going to solve for x. So I'm going to say, okay, log of x is equal to e to the negative x. I'm going to add e to the negative x to both sides. And so I got log of x is equal to e to the negative x. And I'm going to raise both sides. This is natural log, so to undo that, I'm going to do e to the left side and e to the right side. So on the left, I'm going to just get x, and on the right side, I'm going to get e to the negative x. And so now, if I let g of x, our function g of x, equal to e to the negative x, then when this thing is equal to 0, when g of x is equal to x, that's going to be the same location where f of x, that is log of x minus e to the negative x, is equal to 0. So if we can figure out the fixed point of this thing, we're going to get a root of f of x. So this is just some code that will help us find a fixed point of g, right? So here I write a function in R. I'm going to say g is a function of x, and the value it returns is going to be e to the negative x. So the e function in R is exp. So I want exp of negative x. Okay. And then here's the iterative algorithm. I'm going to just start off at an arbitrary location. I'm going to say we're going to start off at 10. I'm going to call that x old. And then we're going to plug in x old into g, and that will give me x new. And here I start off at iteration 0 iterations. I'm going to keep going until the difference between the old and the next value is less than 10 to the minus 8. So a pretty small value. So my while loop will just keep running until it will keep running as long as this thing is true, as long as the difference between the new value and the old value, as long as that difference is greater than our tolerance. Okay, it'll keep running. And then when the difference between the old value and the new value is less than 10 to the minus 8, then we'll quit out of our loop. Okay, so how is this going to work? Well, I'm going to take at the next iteration, whenever I start a new iteration, I'm going to say my new value, we're going to assign that to x old. Okay, so I guess this is my current value. My current value becomes the old value. I'm going to calculate g on the old value, right? And whatever this thing outputs, that's going to become my new value, right? So at the start of the iteration, this is kind of my current value. We're going to make that the old value. I'm going to apply g to the old value. That becomes my new or current value. And then I'm going to add 1 to my number of iterations. And then we just repeat, okay? This is my current value. It becomes the old value, and I apply g to the old value to get it, okay? And that's it, right? And I'm just keeping track of how many iterations I've done. But this is that's it. And I just want to know, okay, is my new value and the old value, is that difference any smaller? Is it less than the tolerance? If it is, we'll quit out, okay? So algorithms that might not always converge, it's a good practice to throw in like a break loop, a little conditional that says like if the iterations go over 1,000, break. Okay, so maybe we'll implement that into the future, but this is what we have here. Okay, so I'll go ahead and I run it, and it says the results are this 1.3098. 1.3098. That's my approximate root. And I can say, all right, is that really a root? Let me plug that in. So if I do log of 1.3098 minus e to the negative 1.3098, I indeed get a value pretty close to 0. I get 9.7 times 10 to the minus 10, so not 0, but pretty close to it. So yeah, that seems to be an approximate root. How many iterations did it take to get there? It took me 19 iterations to get there. Okay. So that's fixed point iteration as a way for root finding. Now, if we assume that this fixed point iteration method does converge, okay, that is that x of n converges to our fixed point A, we can show that the value it converges to is indeed a fixed point of g, right? So given that g is continuous, then, A is going to be the limit, all right, as n goes to infinity, all right? And that value x of n plus 1 is just g applied to x at time n, okay? And so this can also just be, all right, well, this is just going to be g if we apply to the limit as x goes n goes to infinity of x, all right? And just kind of by definition, x then if we assume it converges, then by definition x at time n converges to a, right? So if we assume it converges, then kind of by definition where it converges to is going to be the fixed point, okay? So if the fixed point iteration converges, then it converges to a fixed point. Does it always converge? No, it does not always converge, okay? The convergence of the fixed point iteration relies on the existence of an attractive fixed point. If the fixed point is attractive and your initial value is, quote, relatively close to that fixed point, then the fixed point iteration will converge. But not all functions have fixed points, and not all fixed points that exist are even attractive, okay? So, so fixed point iteration is not guaranteed to converge. One thing that will help is that if you calculate the derivative of the fixed point, okay, if a is a fixed point of g and the derivative or the absolute value of the derivative at a is less than 1, then that location a is an attractive fixed point, okay? However, if the derivative at a is greater than 1, okay, then you're going to end up having a repelling fixed point, and fixed point iteration will not converge. And you'll have an example of this in your homework. All right, so here's an example where we have a diverging fixed point. So here I'm going to take the same function. We want to find where is a root of this function f, okay? And I could say, well, what if I add x to both sides, okay? So here f of x is equal to 0 when, and I'm going to say g of x, okay, I'm going to call g of x this thing is equal to x. So if log of x minus e to the negative x plus x is equal to x, that's going to be where this thing is equal to 0. So we're going to say like, okay, can I find fixed points of g of x? And if I find a fixed point of g of x, that's going to be a root of f of x, okay? Well, unfortunately, this thing doesn't converge. So here I have the same exact code, except I added an iteration limit, and I'm going to say, hey, if the iterations ever go over 1,000, break out of this loop so it doesn't run forever, okay? And then when I run it, then I hit my iteration limit. The iterations go to 1,001, and is this a root when I plug in x new. X new is 7,830. I mean, that could have been the result, but if I plug it into the function log of x minus e to the negative x, I don't get anything close to 0, so that's not going to be a root. Okay, so sometimes you have diverging fixed points, but if you do have an attractive fixed point and you're able to figure out a function g of x, so that when you find the fixed points of g of x, that it equals roots of f of x. This is one way for you to find the roots of a function. All right, so we'll end there.